my dear students. Welcome to Learning Chemistry is Easy and Fun. Continuing with the topic of polymers, today we are doing classification of polymers based upon structure. In order to do that and in order to help you to recall these points easily, I am depicting the classification in the form of three diagrams over here. So you've got one chain, another chain, third chain. They are nicely stacked over each other, right? This is how I have drawn. And if you notice, there is no connection between them. These chains are nicely packed one over the other. Now, if these chains are nicely packed over one another, what will happen to the density of the material? Yes, it will be high, correct? So the density here is high, and because these are forming long chains, will they break easily? No. So that means tensile strength will also be high. What have we got over here is we've got layers of the polymer chains stacked one over the other. Now, it has got high density, high tensile strength. What about its melting point? Because it is being held together by strong forces, strong intermolecular forces. So, let's jot it down as the third point. I hope you have the pen and paper in your hand so that you can note down these points for future reference. Strong intermolecular forces which gives them a high melting point, right? And because of this, they find use in places where we need the substance to be able to hold high weight without breaking down, correct? And the example that we've got is the example of these cans, the toys, the plastic toys. So when these toys, they fall on the floor, they don't break easily, correct? So this is linear polymers, right? You got the name right, and we call them as linear polymers, correct? Can you find out some examples of linear polymers for me? What kind of substances are linear polymers, or what are the examples of linear polymers? Let's go on to the next. Now, if this is called linear, based upon its structure, what will you call the second one as? Yes, it is branched polymer. Branch means you have the main chain over here, and from the main chain there are branches, and from a branch there are other branches, right? Just like you have in the plant root. Now here, because we can't stack them closely one over the other. Why? Because there are branches which are going to keep them away. Now, because we can't stack them close to each other, what will happen to their density? Yes, it is lower than the density of the linear polymers. What about tensile strength? Tensile strength will also be weaker. What about the forces of attraction? Look at the forces of attraction. Are they letting it hold? No, this will crack. Your plastic wraps, your plastic packaging, see, this gives in easily due to when forces are applied onto it. So the intermolecular forces, are they stronger or weaker compared to the linear? Yes, they will be weaker intermolecular forces. What about the melting point? Again, it is easier for us to break the forces of interaction in between these chains. So the melting point will also be lower. So what we've got is, we can describe what are branched polymers and write the points for them. Which will be more soluble in solvents, the first one or the second one, the linear or the branched? Yes, the linear because of its structure. Branched, as they start becoming branched, try and recall what happens to their surface area, what happens to their arrangement. So what will happen is their solubility or interaction with solvents will also decrease, because now they are not arranged in a regular manner as in the case of linear. Here these are spread all around, right? Giving it a branched appearance. What about the third one? Now here in the case of the third one, if you notice here, it is like one chain, another chain. These two chains are connected with each other, right? And they are also connected to chains behind as well as ahead of them. Now because of this close connection, it forms a 3D arrangement, correct? So what is the third category of polymers based upon structure? They are called as 3D polymers, or what else can you call them? They are network polymers. They are networking with each other in all directions, correct? Now what about their properties? Oh yes, you could also call them cross-linked polymers. Now here what is happening is the linking is increasing all the more. They are holding each other tightly, not just in 2 dimensions but in all dimensions. So what will happen to their density? It becomes very high, and it becomes so high that we find them quite hard, right? But at the same time they are brittle as well. So this is where the structure plays a role. So they are hard, rigid, but at the same time brittle. That means if I let this plate fall, will it break down easily? Should we give it a try? Go ahead, give it a try. Experiment at home and look around and find out examples of the 3 types of polymers that we have done over here. Examples of linear polymers is the high density polyethylene that we use. I've given you the examples of toys, of the cans, those materials which are holding a large weight of the substance without breaking down under its strain. I've given you the example of branch chain, the low density polyethylene, the sandwich wraps, the wrappings in all the materials. So this is LDPE, low density polyethylene. The 3D or network, I've given you the example. Yes, it's the melamine, correct? Even your electric sockets and all, the made up of bakelite, they are also examples of 3D or network or cross-linked polymers. Find out what polymers are categorized into the at least three examples of each. Stay with us as we continue with the classification of polymers. I know some of you did not keep a pen and paper in your hand. So what I've done here is tabulated the 3 points or the 3 classifications. So it's easier for you to refer. Next time, don't forget the pen and paper when you come to attend this lecture. Stay tuned, stay connected.